Welcome to our first lesson in our flipped classroom for Chemistry 12. If you fall behind at any time, just simply press pause and resume when you have finished writing what you need to write down. In this lesson, we will look at the relative strengths of some weak acids. So relative simply means how strong something is compared to something else. And we will use their Ka values to explain how they would behave in certain situations when we combine them. So the best way to do this is to look at a few examples. So our first one states to write the Bronsted-Lowry acid-base equilibria for the following reactants. We are given H2PO4- and CO3 2-. And what this question is really asking us is to predict our products. If we look at the reactants we are given, what you should recognize is that H2PO4- is amphiprotic. It has an H at the front. It has a negative charge. That means it could accept a proton or donate a proton. On the other hand, CO3 2- does not have an H at the front. It can only act as a base, so it must accept a proton. What that means is our products are this. As H2PO4 donates a proton to CO3 2-, it becomes HPO4 2-. CO3 2-, which accepted the proton, becomes HCO3-. And that's our solution for this question. Next, we were asked what side is favored. Favored means, if a side is favored, means we have more of that. So basically what this question is asking, what do we have a higher concentration of? Reactants or products? When we answer a question like this, we identify the acids on both sides and we simply compare the Ka values of these things. Larger Ka value means that H2PO4- is better at producing H+, or a stronger acid. Therefore, the products are favored. What is the stronger base? So if we're asked what is a stronger base, we have to simply remember this one rule of thumb. A stronger acid is always on the same side as the stronger base. And we've already identified H2PO4- as a stronger acid, so that means CO3 2- must be the stronger base. Things get a little more difficult when we have two amphiprotic reactants. So here we're given HSO4- plus H2PO4-, and we don't know which one will be the acid, which one will be the base. So what we have to do is same thing as before. We compare the Ka values. Go to the Bronsted-Lowry table, and we find that HSO4- is higher up or has a stronger Ka value, so it's going to behave as an acid. HSO4- donates a proton to H2PO4-. Our products are SO4 2- and H3PO4. Continuing on the same question, so here is that same equilibrium for before. We're asked what side is favored here. Well, in this question, you might quickly look at H3PO4 as one of our acids and say that, hey, it's got 3 H's and it is positive, it doesn't have a negative charge, so it's got to be a stronger acid than HSO4-. But we cannot quickly jump to that conclusion. What we have to do is look at our Ka values again. Looking at our Ka values, we see that HSO4- is the stronger acid. So in this situation, the products are favored. We have a higher concentration of products because HSO4- is better at producing protons. It pushes the reaction to the right. And this is just a quick recap. What's the stronger base? If we've already identified the stronger acid, we know that the stronger acid is HSO4-, therefore H2PO4- must be the stronger base. The last question here we have is, what is the Bronsted-Lowry acid-base equilibria that results from the following reactants? In this situation, we begin with two salts, NaHSO4 and NaH2PO4. Both of these reactants dissociate, and what we should remember about Na+ is highly soluble and is a spectator ion. So if we write the dissociation equation of NaHSO4, we see that Na plus is produced, HSO4 minus is produced, but we're not concerned with Na plus because it's a spectator ion. Same thing happens with NaH2PO4. Na plus is eliminated from the overall reaction. So HSO4 minus and H2PO4 minus are our reactants in this equation. If we write this down, HSO4 minus and H2PO4 minus, again, we could quickly check our Ka values, but what you should notice, this is the exact same question as example 2, just written slightly different. Okay? And that wraps things up for today. Just to remind you of things that we did today and what you should be able to do. When given two weak acids, can you determine which one will act as the acid and which one will act as the base? Can you identify whether the equilibrium favors the reactants or the products? It means which one is in higher concentration. Can you do the above with, if given amphiprotic substances, as well as with salts? Tomorrow, here's what we'll be looking at. We'll be looking at our self-notes or our acid-base calculations assignment, pages 6 to 12, and working on, you guessed it, Hebden questions. See you tomorrow.